Good afternoon, everyone, and this is our final session, I'm pleased to announce. And today we have Tom Charnock, who's the Principal Radiation Protection Specialist at the UK Health Security Agency. And Tom will give us a good understanding of how the PSA code PACE and provide some good examples of how it can be used for its application in monitoring what goes on in the environment from a radionuclide release point of view. I'll pass you over to Tom. Thank you very much.
Hi, hello. My name's Tom Charnock. I am from the UK Health Security Agency, but this time last week it was Public Health England. That's been in the news quite a lot. Most of the radiological protection part of Public Health England has been passed straight over to UK Health Security Agency, so nothing's really changed and is unlikely to change on the short to medium term. We have new email addresses, but our old email addresses still work. A colleague of mine gave a presentation on PACE about 6 years ago. So this is an update of that. PACE is a tool that we've developed at a UK Health Security Agency over quite a number of years now, and it builds on past experience that we've had over decades. And it's intended to help you get over some of the hurdles you need to surmount in order to license and to operate a nuclear power plant. So I'll give a quick overview of PACE, and there really isn't time to get into the interesting undergrowth. It's a synthesis of several models, including atmospheric dispersion and food chain modeling and economic modeling and various other forms of model. But what I'll do, I will sort of step through the stages of a PACE analysis, and that will give you some kind of idea of what it's all about. I'll then briefly have a look at some of the places we've applied it and it can be applied, and finally I'll look at future developments, because PACE is something that we're actively developing and it's changing as needs change. So what actually is PACE? So PACE is technically a level 3 probabilistic safety analysis code for accidents involving a release of radioactivity to the atmosphere. And the probabilistic element comes from consideration of different weather conditions only. So it evaluates the off-site consequences. That's what level 3 means. It picks up from level 2, and it looks at what are the consequences of a postulated release or a set of postulated releases on the environment, on the people who live around it, on the wider population. And so we look at things like what would be the extent of protective actions, the sheltering action or evacuation, how far out and how many people would we require stable iodine prophylaxis for. In the longer term, are we going to need to relocate people? Are we going to need to do some cleanup? And also what foods may need to be restricted to protect the public. It also gives you an idea of what the public doses might be with or without those protective actions, and we look at the various pathways of how people might be exposed. So cloud shine, that's direct exposure from material in the plume as it passes overhead. Ground shine, which is from material deposited on the ground. Inhalation, both of material in the plume and material that's deposited on the ground and then becomes re-suspended into the atmosphere again and is available for inhalation. We look at the doses from clothes, deposition on skin and clothes, and also we look at ingestion of foods. We try to estimate the numbers of health effects that might be associated with a particular accident, both fatalities and morbidities. We look at stochastic kind of health effects, which is basically cancers of various forms, and deterministic. We consider those both with and without protective actions. And on the tail end of PACE, we have an economics model which attempts to put some broad numbers on the economic consequences, both of the accident and also the disruption introduced by protective actions, particularly the evacuations and the relocations and the food restrictions that might have to be put in place. That considers industry, agricultural, tourism, and healthcare, and it tries, as well as doing direct consequences, to do the sort of the knock-off consequences of losing suppliers or losing customers. I will say now that PACE only considers atmospheric releases. It's not for aquatic accidents. And we only are considering the terrestrial pathways, so doses from ingestion of fish are not included, and that kind of thing. So just a quick word about how we implemented it. So as a change from previous codes that you may have seen or may have heard about, PACE isn't a standalone. We decided at the start to implement it inside a commercially available GIS software called ArcGIS Desktop. That's a pretty standard bit of software. It's kind of the Excel of GIS systems, and many environmental consultancies and organizations, government organizations, are familiar with it and have users of it already. And it's the advantage of doing this is that it provides all the mapping and spatial data handling out of the box and leaves us to concentrate on the bits we know about, which is the dose calculations and the health effect calculations, or all the consequence calculations, and not have to worry too much about how to handle spatial data, how to map the results. There are disadvantages. We're kind of tied into this. We have to change as they change their platform. But I think the advantages outweigh the disadvantages. When you get PACE, as I say, it's a synthesis of a lot of different programs. That means models, a lot of different inputs are needed. And one of the design requirements was that it was quite easy to use out of the box, and it does come with a default set of data files that include all your dose coefficients and food concentrations and food ingestion rates and spatial data maps, including population, agricultural production, and economic statistics. So for the UK, at least, it is relatively simple to be up and coming. At the heart of these kind of codes is an atmospheric dispersion model. Like most of these codes, we do include a simple Gaussian atmospheric dispersion model, but I think they're the first ones to try and move away from that and do something a bit better. And we've incorporated or developed links with the UK Met Office Lagrangian particle dispersion model, which is a much more satisfying representation of how radioactive material, or any material, moves in the atmosphere. So I think that's an improvement, and I was pleased to see that the US code MAX have sort of followed us down this route, and they've developed links to the high split model, which is the equivalent US kind of model. Disadvantages: they take much longer to run, and the input data is much more substantial. We're talking gigabytes substantial as opposed to kilobytes. Okay, so probably the easiest way to understand it, and so I don't send you all screaming to the hills, is just to go through the steps of a analysis. So the first step would be to define your source term. That would be the output of a level 2, level 1 sort of analysis. What material is being released into the atmosphere? What sort of forms is it in? What sort of heat has it got? What height is it coming out of? So the first step is to take that information and try and structure that in a way that PACE can understand. And we have developed a small tool to do this. It's the PACE software tool. as it's developed, we put in some basic dose assessment capability inside the tool, so you can have a look at whether you actually need to include all the radionuclides that could be released in your actual analysis. You can see here that for this particular source term, there's a phase where nothing is released that lasts about 12 hours, and then there's subsequent phases where different amounts of other radionuclides release. But if you look at it overall, you can see that for this source term, about 70% of the dose is predicted to come from the iodine, and when you get down to the, I don't know, 8th or 10th most significant radionuclide, they're contributing a small percentage of the overall dose. So maybe you can exclude those. The latest version of PACE allows you to have several source terms, so you could have multiple releases from different sites or different heights, and that's proven to be quite an interesting development, and I think quite a useful one as well. It does give a lot of flexibility. The next stage would be to define the grid that you're going to do your calculation. It'd probably be symmetrical about your proposed site, extending out away from your site. And you can make this as large as or as small as you want, or need to do, depending on the ranges of your consequences. So here it's a few tens of kilometers, but it could cover the whole of the UK. It could cover the whole of Europe if you wanted to. If you needed to go down that route, I hope you're not going to be considering accidents that big, but there is a possibility. As I say, it is kind of geared up for the UK, but we have used it in other countries around the world, in which case you'd have to do latitude and longitude rather than the British national grid, but it's perfectly possible. You would need to supply population and agriculture, but it's certainly doable. So once you've defined the grid, all those spatial inputs like population, agriculture, and economic factors are resampled onto that grid for use in the PACE calculations. So the third step is to simulate the dispersion of the source term, and we do that under for a large number of weather conditions drawn from a historical database of weather conditions, and you can do that with either the name code or the ADEP code. And you probably do that for at least 100, if not 1,000 different sets of weather conditions. And you can see I've just got 10 here, and this is showing the time integrated air concentration of cesium in the first hour for this particular hypothetical incident. I really can't publish real ones. People get very cagey about them. So this is a hypothetical incident at a hypothetical location. But you can see the effect of different weather conditions, the plumes going off in different directions. We've got a very interesting one in the middle where it must be calm conditions, where it's spreading out like a fried egg there. So that is the first stage, and you might, as I say, have a 500 or 1,000 of those different plumes. The next step would be to look at the consequences, and as I mentioned, the consequences could be dose, they could be health effects, economic consequences. Here is the extent and duration of green veg restrictions that might be applied. So each of these plumes is the same amount of material being released, but under different weather conditions, and you can see the range of the impact on green vegetable production is very different, although the material is the same. So I guess the fifth step is where you aggregate that. You have 1,000 plumes, 1,000 different realizations of what might happen for one particular source term. But you're going to need to aggregate that and to summarize that and to bring it down into a small number of descriptive statements about the ranges of possible consequences for this particular site. And we have a number of tools that can do that. The analysis tool tries to define things in a tabular way. So here is looking at the top table is just showing you the maximum residual normal living effective dose over the first year at 1 kilometre. So this is looking at people who spend some time indoors and outdoors. What sort of doses are they going to get over that first year if they're 1 kilometre from the site? So we can see the mean dose for the different pathways, or the maximum dose, or the 95th percentile dose. So that's a dose that 95% of the MET sequences predicted lower than for that particular distance. We can also see other things, like the bottom table is showing the extent of protective actions that might be expected for this particular site, and you can see that the number of people you might have to shelter or evacuate is really rather low, which is good news. People you might have to advise take stable iodine, though we're looking for rather larger numbers. 45 is the mean number of people, but going up to over 1,000. So that gives you some idea, and it'll depend what's the area of interest that you're trying to address is. So that is a very brief view. There's just one last sort of extra to take advantage of the mapping capability that we have, and to try and present the results in a more graphical, hopefully more consumable way. We developed this percentile map tool, and this allows you to present things sort of as a map that might help people consume the results. So on the left, they're showing the probability over all those MET sequences that are calculated that you might have to enact some kind of stable iodine prophylaxis at a particular location. On the right is the kind of the inverse of that, the 95th percentile dose, 2-day dose for someone outdoors. So that's showing you the dose that is only exceeded at those locations in 5% of the MET sequences, and on all the other MET sequences we were predicting something less. So that is really a whiz through what PACE does, and I hope you appreciate this. There's a huge amount of modelling and assumptions under the bonnet there that I really can't explore today, but I'm happy to talk to anyone about them. When we just started developing PACE, it was with an idea of new build. So it's about 10 to 15 years ago, we realized that our old PSA codes were old, hadn't been brushed off since the early 90s, and we needed something new. So we were thinking about the safety assessment principles from the ONR, in particular targets 4, 7, 8, and 9, which relate to the off-site impacts on planned releases. Then Fukushima happened, and we kind of had this new tool, and that enabled us to generate a lot of specific advice for questions that are being asked to us from various UK government departments, and these were questions concerned with UK resilience, how we would cope with our existing fleet would cope with large shocks, and how the UK would be resilient to big events. And in the last couple of years, we've been looking at application of PACE to REPPIR 2019 assessments, which is what I want to briefly talk about in my last few minutes of this presentation. So the new regulations came out in 2019, and they are a sequence of regulations that are updated every few years. And basically the purpose of REPPIR is to ensure that there are arrangements in place to respond to emergencies, both on-site and off-site. The changes in the latest regulations, or the changes that are interesting to me and to use of PACE for this, radiation dose is no longer defined by a specific dose to a member of the public. So much smaller operators are now might be encompassed under REPPIR. Introduce this idea of outline planning zones, and we're not just looking at reasonably foreseeable. we might be looking at larger but much more unlikely kinds of event. Operators make the hazard assessment and prepare a consequence report, and this is passed to the local authority, and it is the local authority that defines the detailed emergency planning zones in these new outline planning zones, using both that report and in discussion with the operator and anyone else they need to discuss with. So it's Schedule 3 that's of interest to me and to PACE, and it's particularly this first one. So the consequence assessment and the consequence assessment report must account for a range of potential source terms and weather conditions. It must tell about different people, how they're being exposed and what they are likely to receive, and what are the important pathways of exposure, and the distance to which urgent protective actions may be warranted for the different source terms. So it doesn't mandate the use of a probabilistic assessment tool like PACE, but it's certainly moving that way. So in response to this, PHE as was, and now UKHSE published this REPPIR 2019 consequence assessment methodology, and the link is there. And this is practical guidance for applying PSA level 3 codes like PACE, or alternatively something like MAX to REPPIR 2019. And if you follow this RCAM, you will fulfill the REPPIR 2019 Schedule 3 requirements. And it's quite a useful document. It provides suggested values that you input into your PSA code for things like location factors. That's the protection people get from the buildings and the way they move about the environment. For the occupancy and shielding and food ingestion and the rest. And it also defines the outputs required. So I won't go through them in detail now, because I see that I'm running out of time, but you can see what they are there, and you can see how the PACE could quite easily generate most of that and help you generate your consequence assessment report. As I say, that report by PHE was neutral. It didn't suggest or mandate a particular code. Currently, we are writing guidance on applying the RCAM with PACE that's going to be published soon, and will include a default set of data, so that really this can be done quite easily when you need to do it. So this is really my final slide. As I say, PACE is under active development, and the focus of what we've applied it for has changed over the years. Though, and it's quite useful that we can it is our code, we can change it as we need to, or in response to the customers. So in the short term, I'm looking at support for different age groups, development of a fetus dose calculation. This is something that PACE can't do, but is a requirement in certain situations from REPPIR. So that's something I'm hoping to be able to put in. What are the doses to fetuses or to breastfeeding children? I've got to port PACE from ArcGIS Desktop to ArcGIS Pro. That's just one of the disadvantages of having PACE embedded within a broader system. We're looking at improving the food chain modeling as well. I think that's something that needs doing. And there's going to be several interfacing enhancements, in particular helping people develop the grid. Users have struggled with what size to make the grid and what size to make the grid squares within the grid, and how big an area to encompass. So there'll be some enhancements to that. And the underlying data that comes with PACE out of the box, we are expanding that and bringing that up to date with European-wide data sets based on FAO Stat and Eurostat. And so that's it. That was a very quick whiz through, and I hope I haven't lost too many people. If there's any questions, I'm happy to take them.
Thank you very much, Tom. That's a great update. I hadn't appreciated it was 6 years ago when we had our last presentation. So thank you very much for bringing us up to speed. Seems to things have moved on quite well and nicely then. A question's come in regarding PACE's development. Does it need to be modified to deal with the exotics that we may end up building, like the molten salt reactors, etc.? Is there any need to modify PACE?
Well, that is an interesting question, and it is one we're thinking about. You could use it out of the box. I think there's two areas in which it might struggle, if I'm honest. It's whether the radionuclides that are released and the forms of those radionuclides are similar to what you might term the traditional reactor source terms, or whether they're strange and wonderful. It was nice to hear yesterday that the Rolls-Royce SMR is a PWR and quite a large one, so that may be not too hard for PACE to encompass. I think the other way that PACE and all PSA codes might struggle with small modular reactors is the small side of things. If you have if you have a large release and it covers a large area, it's less important where people actually are, because there's a certain amount of smoothing. But if you're dealing with a small area, and particularly if it's a small complex area, it probably struggle. Both the data, it would be worth getting something a bit more high resolution on the population front, and the representation of the atmospheric dispersion at those short distances and possibly complex around buildings, it may be difficult there. So I'll be brutally honest with that. It wouldn't be that hard to introduce a short scale model, but it would, the inputs would become harder because you'd have to be defining some of those buildings and short-term, the things that affect things on the short term rather on the short distance rather than the longer distances. I hope that makes sense. So
yes, of course. So there's clearly some thought that needs to be put into looking after that, in terms of the exotics and how they could perhaps be modelled from a release point of view. Just two other questions, actually. Quite an interesting one here. Just stop and visualize this one. The question is all about moving source terms. What someone's thinking of here is that if we do have ships with a nuclear core in it, and it springs a leak, and there's a plume coming out of it, would PACE be able to model a moving source term? Leaving aside, you'd probably drop the anchor and keep the boat out at sea rather than bring it into land.
I was going to say, you'd have to know what the boat is going to do. Is it going to stay still? Is it going to go to the nearest port, or is it going to head to the Atlantic and scuttle itself? If I had to do that tomorrow, then I would probably model that as a sequence of sort of point releases. As I say, you can now have a number of locations, any number of locations. So you could have 20 point releases moving down the English Channel, for example. That would be the closest I could get. You couldn't at the moment model a continuous release, but you could certainly have a stab at it, and if it was moving slowly, I think that would be a reasonable approximation, given that you're probably far from land anyway, and there'll be a lot of mixing before it actually impacts with a static population.
Very good. And finally, just looking at the REPPIR revisions to the regulation there, one of the ones you mentioned there, which it sounds rather interesting, is that the local authority now would be charged with defining the DEPZ, Designed Emergency Planning Zone, etc. How would that work in practice? I'll take the point that the licensee would have to provide some form of information report, which may include some PACE information. But how would that work in practice? Would they have to get the technical competency in-house to be able to do that?
I don't think they would need they would do it with advice from the operator and from people like us. I think they have a lot of competency in contingency planning as it is, and in resilience they have to deal with, you know, your floods and your fires and things on an everyday basis. The detailed plan is about marshalling your resources and coping with your displaced people. So I think they are probably best placed to do it. But as I say, it's a collaborative process. It's not here's your report and off you go.
Okay, thank you very much, Tom. Really appreciate that update, and there's some good thoughts there for the future as well.